And there's other things there on YouTube that you can go to see. And here we are, course, Physics 220. There are 2 videos there now. There will soon be, I'm supposed to stand up here when I'm using the computer, but that's all right. Anyway, so there are 2 lectures on there now. There's 2 videos. We load them up. The crew takes them over there to the IT guys after every lecture, so they'll get downloaded within a couple hours after the lecture, so you can find them then if you happen to miss. All right. So let's go ahead and get started. Let's turn on the lights. Listen to a few folks that are usually here, but hopefully they'll come in. We can get them on the screen and get them in the lecture thing. Chastise them in public. Get their name on YouTube. Yeah, like Melissa. This is Melissa Briggs, by the way, for all you millions out there that'll be watching this video. All right. Okay. I want to turn off the projector. I'm going to turn off the projector now. There we go. All right, now, a few things that we left off last time. As we left off last time, we were getting ready to do Gauss's law, but the first thing we needed to do was to look at a parallel plate capacitor. Come on in, Naomi. Let me get Naomi her quiz back. There you go. And Melissa, you can get your, where did Melissa run off to? Oh, okay.
Trying to be inconspicuous.
Inconspicuous, right. No, you can't. Won't allow it. All right, one thing we need to talk about is the parallel plate capacitor, because it's kind of a cool thing. All right, and I'm going to draw this. This is supposed to be 3-dimensional, and I'm going to draw it 2-dimensional. Okay? I could go to the slideshow, but that about kills it, so we won't. All right, now, here we go. Here's one plate, and it's like going into the wall. All right? And it's got positive, I'm going to put 4 charges there. Okay? Now, on this side, and usually these things are really close together. They're supposed to be shown pretty far apart for clarity. But usually they're very, very close together. So I've got a question for you. If I got a bunch of positive charge here, and it's pretty, and this is a conducting surface over here, what kind of charges are going to build up over here? What's that? Oh, my microphone's off? How do I turn it on? Oh, I turn it on here. Oh, I'm sorry. Is it on now? Can you hear me now? Okay, good. All right. So we had no sound for the first part, but that's all right. You're the ones that paid $1,000 to be here, not people there. All right, so now, and you heard it. So, here we go. 2, 3, 4. All right. So a bunch of negative charges would build up on that side. Okay, now, if we're going to draw electric field lines, which way would they go? Would they go from the left side to the right side or from the right side to the left side? Which direction would the electric field lines be going? Left to right. Right. Okay. So you'd look like this. So you got this is our E field here. And of course, this is just a representation. It's a solid E field that goes from there, from one side to the other. Now, here's the deal. We talk about charge density, okay? We talk about the charge density. So we've got a positive Q over here. We've got a negative Q of charge over here. And the actual charge density, sigma, we call it, is equal to the Q divided by A. Okay? That's what we call the charge density. Okay? This is called the charge density. Now, the other thing, too, that you need to know about what's going on in inside of these parallel plate capacitors is this. The E field, the strength of the field right here is the same as the strength of the field right there. Okay, it's uniform throughout. All right, that's very different from our good old point charge. Let's just take a positive Q point charge right here. Now he had electric field lines coming off of him like this. They're all uniform and everything. And the further we get away from him, what happens to the E field? It decreases, right? It goes down because his E field is equal to this. The magnitude of the electric field for him is K Q over R squared. And the further away we get away from it, right. It goes down. Sorry. Had a brain vapor lock there for a minute. All right, now. And so, but this one, the E field stays the same, and the E field inside a parallel plate capacitor is equal to Q over A over sigma. Not sigma, over that little echo knot. Okay? Which equals sigma over that echo knot. Where echo knot, remember, is the permittivity of free space. All right? We didn't talk about that last time, and it's a key thing. The key thing is that the electric field, the strength of the electric field is the same everywhere inside that parallel plate capacitor. Okay? All right. And eventually we'll learn that a parallel plate capacitor works just like a battery. All right, now, I'm going to write some English on the board. Okay? Here are some big ideas that you need to know about electrostatics before we get into Gauss's law. What I'd like to cover today is Gauss's law, the end of chapter 18, and the first two sections of chapter 19. All right? And then we'll finish chapter 19 on Monday. Then on Wednesday, we'll do a quick review, and then we'll count off by threes, and you all can get together and take the test. Take a group test on Wednesday. Okay? All right, so that ought to be entertaining for me, if nothing else. But anyway, here we go. Okay. At equilibrium, here's idea number one. At equilibrium, now what do we mean by equilibrium? That's when remember when we had, like, let's say we've got a charge, this guy has positive 3Q, and then we bring him in we bring in this negative 2Q like this. What happens here? Basically, we wind up with a thing here that's got a total charge of, on both of them, of a half a Q and 1/2 Q, right? Now they're in equilibrium. It's all good, right? Okay, so at equilibrium, under electrostatic conditions, all right, any excess charge resides on the surface of the conductor. Okay? That's the first thing. So when I do this, if I touch all this, in other words, let's make this a -3 and this a +2. And so when I get them all touched together, they got a negative charge on them. So I take this disc away. I take this little cylinder away. So he's got all these little negative charges right here on the surface. And those negative charges add up to a -1/2 Q, whatever that Q was to start with. Let's say it's a half a coulomb. That'd be one heck of a charge. Ouch, if you touched it. But because there's a lot of amps there that would go through you. Okay, but they all reside on the surface. Okay, so let's think about that for a minute. Let's look at this sphere. Let's look at this guy. Here's a question for you. Should have been a quiz question, but I got other quiz questions already made up, believe it or not. All right. What do you think the electric field is on the inside of this guy? What would be the electric field? Catherine says 0. Anybody think it's going to be some convoluted thing? Some convoluted physics thing? It's actually it's very simple. In other words, the electric field lines are coming into here and they're stopping. Any outside electric field lines are coming into here and stopping, so she's absolutely right. Inside here, E equals 0. Anywhere inside there. Anywhere inside, because all the charge is on the surface, so the electric field on the outside is all coming and collecting on the outside of this thing. Okay? And nothing's getting through to the middle. So, big point number 2 is at equilibrium, under electrostatic conditions, again. And what we mean by that, electrostatic condition, is there's no charges moving. There's no voltage here creating amperage that's flowing. All right? We're just under electrostatic conditions, which don't really happen, but it gives us a launching point to learn about electricity. It's kind of lays the foundation. Okay, at E equals 0 within the conducting material. Doesn't matter if it's a shell, or it doesn't matter if it's a solid ball. E is equal to 0. Okay? Now, let's combine this idea. Now what we're going to do is we're going to put the idea together, the parallel plate capacitor, along with this conducting sphere. We're going to put this conducting sphere on the middle. 1, 2, 3, 4, 5. Put a conducting sphere in here. We'll have 1, 2, 3, 4, 5. And that conducting sphere changes the, even though it's charge neutral when we put it in there, guess what happens when we stick it inside that electric field? Well, all the little negative charges are attracted to this side. So all the little negative charges line up over here. Let's just put 5 of them. 1, 2, 3, 4, 5. So they're right here. Okay? And then what happens? All the positive charges, 1, 2, 3, 4, 5, line up over here. Send it like that. Okay? But what's going on inside that sphere, though? What's the electric field inside the sphere? 0. 0. And there's a fancy vector calculus way of proving that, but we're just going to tell you, okay? And because I can't do that. All right? I could. Sure, I could. But anyway, so that's on the inside there, and it's equal to 0. Now, what this does, this has some very practical applications, okay? Like, say you're working on your computer, and you're drying your hair at the same time, okay? Not that that would happen, maybe, you never know, okay? Well, or you're, back in the day, they didn't have very good shielding things, and so whenever Mom ran the mixer when she was baking a cake, when you were trying to watch Gilligan's Island reruns when you hurried home from school back in the 70s. That's what we did. Okay. What would happen when Mom would turn on the mixer? You get all this interference, and you couldn't see Mary Ann anymore. All right. But anyway, until she turned off the mixer. That's because that mixer created an electric field that was going out. All right. And it was getting into the circuitry of it was interfering with the circuitry of the television. All right. But with this shielding thing, if you've got a good shield around all your circuitry, in other words, you put all your circuitry inside this little ball here, this conducting ball, not a wooden ball. Most people think, oh, well, I'd want it inside rubber or something like that. No, you don't want it inside that because the electric field just passed through that. Okay. What you want is you want it to be a conducting thing so that all the electric field collects on the surface of it, and what's going on inside isn't touched, doesn't harm it. What's that? Yeah, exactly. Yeah, that's what that box is, protect that circuitry and stuff. Okay, so that's point number 3. The conductor shields. I left my notes over here. Gotta walk over. Any charge shields any charge within it. Okay? From the outside electric field. Okay? That's a pretty important consequence of that whole thing. Okay. Now the last point. Last point. The electric field. So let's just draw our ball again. You cannot teach electrostatics unless you know how to draw a sphere. Okay. All right. And okay, we got a conducting sphere. Let's say it's not charged neutral; it's got a negative charge. So now let's put a positive charge on it. So we got it's say it's positively charged. So all the excess positive charge is hanging out on the outside. Now the electric field lines we know look like this. They're coming out of there, and when they first leave the surface, they're at a 90-degree angle. Okay, that's the last point. So that leads me to concept example number 14. Not 16. I want 14. Not 15. 14. Okay, it says here, a charge is suspended in the center of a hollow, electrically neutral spherical conductor. Okay? So, let's make this spherical conductor. Well, let's just draw a cross section. Let's draw a cross section. He's hollow. So let's just put a little spherical shell around him right here. And he's neutral. He's electrically neutral. So that means every little proton is hooked up with an electron. All right? And let's go ahead and put a positive charge in here. Let's put a positive Q in here. Now, what's going to happen? The question is this. Show that this charge induces a charge of negative Q on the interior and on the interior surface, and B, a charge of positive Q on the exterior surface. Why would a positive charge like that suspended in the middle, if we could do it, suspended in the middle of this neutrally charged conducting shell, what they mean is, why would all of a sudden negative charges be right here on the inside? Why is that?
They're attracted to the positive.
Yeah, they're attracted to the positive charge, right? And he's sending out a little E field. He's going, remember, little eharmony.com here to these negative charges. Going, come to Papa, and that's what they're doing. So he's got this kind of thing here, going here. Okay? But if they're showing up here, then what's on the what's on the surface? The positive charge. The positive charge, it's like this. So we've got these positive charges out here. And so guess what happens? We all of a sudden get just a continuation of this guy's electric field on the outside because it's a thin shell. Okay? What if we have, now what happens to the electric field on the inside of this thing if we take away the positive charge on the middle? What happens to the E field in the middle?
Zero.
Goes to zero. Right. Goes to zero. Okay. Now, we're ready for Gauss's law. Okay? We are ready to attack Gauss's law. All right. We're going to talk about two things here. We're going to put two ideas together. We're going to talk about the electric field, which we've already talked about extensively. And it's probably still mushy in your head because this stuff is not easy. Electric field. We're going to combine the idea of electric flux. No. We're going to combine the idea of the electric field and the surface area it passes through. There we go. And the surface area it passes through, and then these guys will go into this little box called the idea of the electric flux. Not the 15 gigawatt flux capacitor from Back to the Future. Okay. That's a classic example of Hollywood taking scientific terms and just kind of throwing them together and coming up with the flux capacitor. Because we know there's a capacitor and they know there's flux, but there's, anyway. All right. Okay, so we're going to, and the electric flux, so we've got surface area, flux, electric flux, and this will give us Gauss's law, which I talked a little bit about on Wednesday. I talked a little bit about it on Wednesday, and I looked out there, and it looked like you all just had a shot of Novocaine after I said it, because it was like, whatever you're saying. Okay, so let's take a look at this. Now, let's go ahead and keep this idea here with this guy, because the electric field coming out of here, remember, it's not like all of a sudden it's all bunched up here and then there's just a little bit coming out down at this end. It's coming out uniform. Okay? The electric field coming off this thing is uniform. Now, one thing you need to know is, do you remember the surface area for a sphere? Remember from Miss Crunchmeister's geometry class what the surface area for a sphere is? Any of you taken calculus before? You remember what's the area, what's the volume of a sphere? Remember that? Not 3/4, but 4/3 power cubed is the volume.
Surface area is 2
Nope. That's the surface area. That's the area of a circle. What's the area of the sphere? What we do is we take the first derivative of this guy. I know this isn't a calculus class, so the surface area of a circle is equal to 4 pi r squared. In other words, you take your area of a circle, multiply it by 4. And that comes up with the surface area of the circle. All right, so of the sphere. So in other words, remember when we talked about that the charge coming out of here, you have a total charge, the surface density would equal the Q over the A, right? In this case, and we said that E is equal to Q over A. Well, we said this. We said that E is equal to sigma over echo naught, like that. So here we go. we get EA then, and this is your electric flux. Is equal to the total charge divided by echo naught. Okay? And another way that we write that is this way. This big phi guy. Big phi is equal to Q over echo naught. Now, that Q is the charge enclosed. That is the big idea there too. Q must be charge enclosed in the surface. Now this is all abstract stuff that we're talking about here. In other words, what physicists did, what Gauss did, he told the physicists, Gauss was actually a mathematician, but what he told the physicists to do, hey, if you want to deal with this stuff, just by the way it works, draw an imaginary surface around it that you can work with, like a sphere, a cylinder, or a cube around whatever charge configuration you have. And because of those other laws that we gave for electrostatic conditions, you can figure out what the electric flux is for the thing. And then what we use that for is we want to determine what the electric field is maybe out at some point here. Okay? All right. So it's got to be the enclosed charge. So here we go. Let's do example 15, and then let's do homework problem 52. All right? Which is waiting for you, I'm sure, there on Wiley Plus. Sinister homework problem. Remember, Q is the charge enclosed. So let's take a look. Q is the charge enclosed inside the surface. And we determine the surface. We draw it. All right, so here we go. It says we've got a thin spherical shell. Let's draw our good old thin spherical shell again. Little physics joke. You ready? I should probably say stop rolling, but it's okay. We'll let it go. How does a physicist answer the question, why did the chicken cross the road? He says, first assume it's a spherical chicken. Sorry. Okay. Well, anyway. Yeah, that was the joke, by the way. That was it. I know it's not near as funny as my 9 centimeter thing, but anyway. We got a thin spherical shell with a positive charge. It's positively charged on the outside. Okay. And it's got a radius r. Radius of big R. All right. Now, what we want to do is we want to find the electric field at a point out here. At a point out here at R. The distance R. This point P, what does E equal? At P, what does E equal? Okay? We can do this. We have the tools, we have the talent. So what we're going to do is, we're going to draw a sphere. We're going to draw our sphere, an imaginary sphere around here like this. Okay? All right? And we're going to say, okay, I know this. I know that the electric flux caused by this sphere is equal to EA. E is what I'm after. Is equal to the charge enclosed. Look at here, we got the charge enclosed, whatever that happened to be, with that Q over sigma. Well, not over sigma, I'm sorry, over the permittivity of free space, which is a constant. Okay? That's in your book somewhere. All right, so how do I find E from that? What should I do? From that simple algebraic expression there. How do you find E? It's not hard. Don't be bashful. Yeah, just divide by A. Right, just divide by A. So E is equal to Q over A E. The hard part is, what's A?
4 pi squared.
There we go. 4 pi r squared. So this equals Q over 4 pi r squared times echo naught. Oh my goodness, look what we got here. I love it when a plan comes together. Do any of you remember what 4 pi echo naught is? 1 over 4 pi echo naught? Remember that? Y'all haven't worked enough problems yet to know. K. There we go. It's K. So this answer is actually KQ over R squared. Have we seen that formula before? Yeah. This is how we found the electric field for just a point charge. Now we've got this sphere, and it turns out to be about the same thing, because we're using a sphere. Okay, so now. Oh, and they also wanted us to find out what is the they wanted us to find what's the electric field inside the shell. What would be the electric field like right at a point right here? What's that electric field? How much charge is, okay? What is it? 0. Yeah, it's 0. But so again, just to hammer home this idea of charge enclosed, let's draw a little sphere in there. How much charge is enclosed inside of here? None. There is no charge enclosed inside that imaginary sphere we decided to draw around that point, with that point on the exterior. Okay? That's how you guys are ready to take Physics 460 now, because that was one of the hardest parts of that class, was getting that charge inside. Okay, now, so let's get us started on problem 52. Homework problem 52, which says 2 spherical shells. Oh my, they're trying to be slick. Okay, but your Poly Plus, remember, is going to give you different charges. All right, so let's try this. Let's do problem 52 over here. Oh, wait a minute. Did I pass up a quiz? Oh, no, we got a quiz opportunity coming up here. Won't be near as hard as this. See, since I'm being filmed, I have to like plan out the class for it. Like, oh dear. Don't want to miss anything. All right. Here we go. Here's what problem 52 says. Check for my glasses. Oh, I did bring my glasses, but that's all right. My arms are still long enough. Okay. It says here, 2 spherical shells have a common center. Okay, so let's draw 2 spherical shells with a common center. Means they're concentric shells. Okay? And they're shells, so this has a thin thing here, and this will have a thin thing here. All right? It says a charge of negative 1.6 times 10 to the negative 6 coulombs is spread uniformly over the inner shell. So negative 1.6, it's got a negative charge spread uniformly. So it's got a negative charge. And we'll say this, Q inner equals negative 1.6 times 10 to the negative 6 coulombs, or negative 1.6 microcoulombs. Okay? Now the outer shell has a 5.1 microcoulombs positive. Q outer equals positive 5.1 times 10 to the negative 6 coulombs spread evenly on the outer. Okay, you get the idea. All right, now then, let's draw our electric field lines. What they want us to do is the inner radius here is 0.05 meters. Now your inner radiuses are going to be different. And the inner radius for this guy, the radius for this guy, I think is 0.15 meters. Yep. Not 1.5, but 0.15 meters. Okay, so we've got those two. Ri is equal to 0.05 meters, and Ro is equal to 0.15 meters. All right? Now then, let's just take a look. It says find the magnitude. We've got to find three things. Find the magnitude and direction of the electric field at a distance from the common center at point 2. So point 2 would be out here. We need to find the electric field out here at 0.2 meters. They want us to find the electric field at a point, part B, is find the electric field at 0.1 meters. That'd be right around in here. At 0.1 meters. And they want us to find an electric field at 0.025 meters. Right there. This point P right here. Let's start with that one. When R equals 0.025 meters, what's E equal? Right here. Inside. 0. Right. E is equal to 0. Now, let's do the one let's do this next one. This guy right here. Okay, we got to draw some electric field lines here. Hopefully I can draw this so that it looks halfway decent. Okay. Let's draw some electric field lines here, just a couple of them, just to give us an idea. So they're going to come in here and marry up with these guys like that. Okay? So you got this E field coming in, and you also have these guys are radiating out this way too. Okay? But the ones going in are only marrying up with the negative charge that's here, with the negative 1.6 microcoulombs, right? Okay, so for this point, for R equals 0.1 meters, R equals 0.1 meters, what is Q? What's the enclosed charge? What's Q? Enclosed. What's the enclosed charge for at R equals 0.1 meters? David says negative 1.6. You going to stick with that?
I guess.
Okay, good. I like a man with convictions. And he's right. He's right. It's negative 1.6 times 10 to the negative 6 coulombs is the charge enclosed. Okay? So to find the E field, we go, oh, okay. The charge enclosed is equal to negative 1.6 times 10 to the negative 6 coulombs. And so E is equal to Q over echo naught times A. Again, this is shells, so what would A be in this case? A is equal to 4 pi times 0.1 squared. Because that's our R. And the rest is just fiddling around with the calculator.
Well, wouldn't it be more positive since you have like a structure of positive on the outside?
We do it. Oh, Catherine's got a great question. We've got a stronger positive on the outside, or there's more positive charge on the outside. Where's that extra charge radiating? Outward. That's these guys, what's left over. So that sets us up to do this guy. And we'll look at the charge enclosed. Okay? So let's take a look R equals 0.2 meters. When we take a distance of R equals 0.2 meters. Okay? The big question whenever you're doing Gauss's law to find the electric field is, what is the charge enclosed? Q, enclosed in this case. All right, Catherine, what would be the Q enclosed in this case? Okay, it's part of it. What else is enclosed in there? Yes, and a minus 1.6. Exactly. So we wind up with a Q enclosed of 5.1 microcoulombs plus a negative 1.6 microcoulombs. And so the total charge enclosed then becomes, if I have $5.10, I spend $1.60, how much money do I got? $3.50, right? 3.5, right? Is that right? Yeah. 3.5 positive. And that, this electric field, we wanted to know which ways we'd say radially inward when they ask for the direction. It's radially inward. For this one, we know that we can look at the electric field here and we see that it's radially outward. And we wind up with the same thing. E equals Q enclosed over echo naught times 4 pi. And in this case, we've got 0.2 squared. Yeah. Now, when you go to do this problem this weekend or on Monday morning or whenever you're going to do it, Wiley Plus screws it up because they give you like 2 points that are way out here. Or they give you a bunch of points that are inside here. And so if they give you nothing, in other words, if they give you nothing but points between 0.05 and 0.15, if they give you those R's, then the Q enclosed is equal to negative 1.6 microcoulombs. Okay? If they give you R is less than 0.05, Q enclosed is equal to 0. And if they give you R is greater than 0.15, then the Q enclosed is equal to 3.5 microcoulombs. Okay? It's kind of a difficult thing. It's not real easy. It's not real easy.
Question.
Yes?
Do those two spheres between there, do they act as parallel plate capacitors?
Yeah. Yep. But there's some extra charge that's sending that E field off that way. Yep. It sure do. So the E field in the middle here is uniform. The E field in the middle. Oh, wait a minute. I've got to be careful because if we actually move in closer, the E field changes, right? If we move closer and closer and closer, the E field changes. So, no. The answer is no. They will not, because what did we say about parallel plate capacitors? The E field's uniform. Okay? So, good question. Yes?
What's the little E naught like on that equation over there?
Permittivity of free space, it is equal to this.
8.85.
8.85 times 10 to the negative 12, right? Something. It's equal to E naught is equal to 8.85 times 10 to the negative 12. What are the units for it? Coulomb
squared.
Per Newton meter squared.
Per Newton meter squared. Coulomb squared per Newton meter squared. That's what, it's just a constant. Just like our good old gravitational constant, all those things. And K is just that flipped over, K is equal to 1 over 4 pi E naught. So you multiply this by 4 pi and flip it over, and you got K. And look, luckily, we're multiplying by 4 pi each time because we're doing a sphere. Okay. All right. Okay, well, that was about as fun as an all-night dentist. So let's, but it was actually pretty good stuff. That's good stuff. Now, let's talk about the electric potential energy. Okay? And it took me 3 years of teaching this course to finally get my head around electric potential energy. I was always hiding behind the math, acting like I knew what was going on because I would just do the math and go, okay, well, that's what the answer's got to be, and not really know what they meant. And it's actually not that hard. Okay, let's start off. I like the way they started off. Oh, I forgot to give you all a quiz. Here's question 1 for the quiz. Question 1. Here we go. And it's going to take no real computation. I'm going to draw 2 things here on the board. Here's question 1 for your quiz. All right, there's one picture, okay? These dotted lines represent the Gaussian surface that I decided to draw around that, okay? Here's the next picture. And I'm going to draw my Gaussian surface, include these 2 charges here. Okay, here's the question. The drawing shows an arrangement of 3 charges in parts A and B, different. This is A, and this is drawing B. Okay. In parts A and B, different Gaussian surfaces are shown. Through which surface, if either, does the greater electric flux pass? Remember, electric flux is E times A. Which one? Basically what they're looking for, which one has the greater electric flux passing through it? Or are they the same? So take a minute. I don't want you to get too hung up on this. So what I'm going to tell you right now is the area for A is the same on both of them. Okay? We'll just arbitrarily say that if you said, okay, flux is equal to EA, you'll see the area is the same for both of them, even though the picture doesn't show it that way. So, when the flux is greater, is A greater than B, B greater than A, or is A equal to A equal to B? Of course A is equal to A. It's a reflexive property. All right. Okay, so that's question 1. We'll get to question 2 here in a minute. Okay, you should be... Oh, Dr. Vogel told me not to say okay anymore. I just said it 8 times, and that's all right. Now, let's talk about electric potential energy. This last 10 minutes or so. Let's just get kind of started. As we zip on good old summer school as we zip through some big ideas here. And let's go straight to the electric potential energy circuit. All right, here we go. Now, and then we'll end with quiz question number 2, and I'll start that at about 7 after. So here we go. I got a basketball. Okay? I got a basketball up here at a height A. And it's being held by a string or something. And I cut that string, and it falls down here to a height B. Did any work take place as it moved from A to B? And what did it? What did the work? What created the force? Gravity. Gravity created force. Is the work in this case positive or negative that gravity did? The work done by gravity would be positive because it's going in the same direction as the force. Right? Because the movement is going in the same line with the force. First, and here's the last quiz question from semester 1. I forgot what it was. Okay. I guess we won't have a... is gravity a conservative or non-conservative force? Does it depend upon the path, the change in gravitational potential energy? It's conservative. Okay? In other words, remember, if I've got this marker held right here at this height, and I want to change its gravitational potential energy, in other words, I'm going to do positive work by my arm to raise the force up to here. It doesn't matter if I go like this. The change in energy, once I stop, didn't matter about the path. Okay? Now, the friction caused by the air molecules and everything, that was non-conservative, so that did depend upon the path. But the actual gravitational potential energy didn't depend upon the path. Okay, so the work done was positive. The work done to go from A to B, from height A to B, was equal to mgHA minus mgHB. Okay? That was good old positive work. Remember, gravity or energy. Next question from first semester. Is energy a scalar or a vector? Scalar. It's a magnitude. It's just difference in magnitudes, right? Now some will be positive, some will be negative, stuff like that. Okay, now the electric potential works the exact same way, except we got so used to in chapter 1 where gravity always was radially inward, was always going towards the center of the earth, was always going down, that we just get in the habit of that. But remember, let's just take a look at our parallel plate capacitor here. We take and let's draw it this way. We've got positive, 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 positive. Negative, 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 negative. Okay, I think I matched it up. No, didn't. Got too many negatives. Okay, there's my parallel plate capacitor. Now, if I put a positive charge here, a proton there, which way is it going to go? It's going to accelerate towards that plate on the bottom, right? It's going to go this way. All right? But what's going to happen, though, to a negative one? If I put it down here, negative charge is going to do what? It's going to go up. Even though the electric field is going against it, the force it feels is going that way. All right? The force this guy feels is going this way. So the parallel plate capacitor is doing positive work on both of them. However, the actual objects are losing potential energy. Does that make sense? It's just like, this is what I had a hard time getting my head around, okay? Until one of my colleagues downstairs said, well, it's just like the basketball goes from here to here. It loses potential energy. But positive work was done to it. Right? Because it's losing potential because what's going on? It's accelerating. So therefore it's gaining speed. It's gaining kinetic energy. All right? So it's losing potential energy. Same thing here. This little proton here is going to be gaining kinetic energy as it's moving, but it's going to be losing potential energy. All right? And energy is conserved. Energy is conserved. Okay. So,
I'm sorry, can you talk about the negative electron going up? What did you say was positive?
the work done is positive
Work is positive.
because he's going in the direction of the force, but he's going to lose potential energy. He's losing potential energy because he's gaining kinetic. Okay? Because he's going to be accelerating up towards that plate. All right? I don't know why that was so hard for me, but it was. Because there's a lot. Because I think one of the problems is because we're so used to gravity always going down. This time we've got something that can actually fly up. Okay? Because this force, I didn't have you compute it, but the electrostatic forces are so much stronger than gravity anyway. We pretty much ignore them when we're dealing with gravitational forces. Okay, so here's the question. Here's quiz question number 2. All right? I think you guys are ready. I think you can. Oh, no, you're not. You're not ready. Hold on. You're not ready. All right, now, the next thing that we're going to deal with here is I got a bunch of positive Q up here. I got a bunch of negative Q down here. Okay? Now, that's given me a potential difference. All right? So in other words, what we're doing here with electric potential energy, okay, with electric, this is called the electric potential energy. The work done by electric potential energy is equal to the electric potential energy of A minus the electric potential energy of B. So far, you have no idea how we actually measure that or what variables go into that electric potential energy. It's measured in joules, okay, for our purposes. A lot of people do it in electron volts and stuff like that, which we'll get to in a minute. But it's measured in joules. Okay, now, let's do this. Let's divide, let's say we've got this nice little positive Q naught here. Let's divide this all by a positive Q naught. Okay? Now, what I've just done is this. This is the same as VA minus VB equals the work that the electric field did from A to B divided by Q naught. This is volts. This is volts. Volts is measured in joules per coulomb. Okay? Volts are measured in joules per coulomb. Now the actual change in potential. Now, what about this change of potential from A to B? This guy's going from here to here, but here's actually the way we do it. We say the change of potential. Now, don't want that B there, is equal to VB minus VA. And when I flip these two around, what happens to this guy? But algebraically, he becomes negative, right? If I go, I want to do VB minus VA now, then this side becomes negative. Just like 7 minus 3, if I go equals 4, if I go 3 minus 7, that equals negative 4. Okay, so we're doing the same thing. Is equal to negative WAB over Q naught. Okay. All right. And that is measured in volts. It's joules per coulomb. It shows how much energy. Actually, what you're doing is you're showing a volt tells you how much energy the electrons have as they're going through a wire and stuff like that. Okay. It's the measure of the electron energy. That's why they have electron volts too. Now, EPE on the other hand, the electric potential, and you'll also hear this called the potential. As the 460 physics book, the Griffiths physics book says, this is a horrible use of English here because this is not the potential energy. It's the electric potential. It's voltage. Okay? Engineers don't even mess with it. They just call it volts. Okay? They just call it volts. Okay. That's the potential. And here's the deal. The change in electric potential energy is equal to Q, whatever that Q naught is, times delta V. All right. Okay. Or Q, the change in electric potential energy, is equal to VB minus VA. Okay, so here's the last second quiz question. Okay? By the way, what was the answer to the first quiz question? We're going to be easy the first week of school. What was the answer to the first one? Was it, everybody get the same?
Same.
All right, we're going great. 230, good. Now, here's your next quiz question. Now, Gary Lezak told me last night on the news, he said that we got about another week of violent weather here in Missouri and stuff. So, let's do a violent weather problem. Here we go. It says here, during a particular thunderstorm, the electric potential difference between a cloud and the ground is V cloud. Let me just carry this over here. V cloud minus V ground is equal to 1.3 times 10 to the 8th volts. Okay? That's the potential difference. It's not the electric potential difference, it's the potential difference. Now, it says this, with the cloud being at the higher potential. Okay? Well, of course the cloud is at the higher potential because we got a positive number here. All right? So now, what is the change in an electron's electric potential energy when the electron moves from the ground to the cloud? Okay? In other words, lightning is basically a huge parallel plate capacitor. Really what it is. You got cloud, ground. Okay? Ground's negatively charged. Well, it's zero most of the time, but because of the iron core of the Earth, you can get electrons kind of pool up in one place. All right, so now we've got an electron, where Q. What's the charge of an electron again? Real quick. Remember? It's minus E, which will be negative 1.6 times 10 to the negative 19th coulombs. Yeah, somebody, the 0.2 is also good. That's a little more precise. We'll just use negative 1.6. That's good. All right, so QV is equal to that. Now, so there's little electrons hanging out down here. And he's going to go zipping up there. Remember what they're asking. Remember what they're asking. The question is, What is the change in the electron's potential energy, his EPE? What's the change in his EPE as he goes from the ground to the cloud? Okay? Okay. Now then, is that electron, is he going to gain potential energy or lose it? Gain or lose? How many think it's going to be gain? Okay? How many think it's going to be lose? All right? Let me think. No. Now remember, which way is the force going? Which way is the force going? No, the electric field's going down. Which way is the force on this guy going? Up. So the force is going up. Which way is he going? Up. So therefore the work is positive, so therefore his potential energy is negative. He's losing potential energy. Okay? Because the work is positive. In other words, it's just like dropping the basketball, except this time gravity's going up, taking him up. So he's losing his potential energy because he's gaining kinetic. All right? He's gaining a tremendous amount of kinetic energy. So your answer should be negative, and when you get done, the EPE is just going to equal QV. So you take that negative times pi. You can't go wrong that way. Okay? All right. Yeah, it's something, you have the weekend to kind of get your head around that a little bit. And while you're working on it, I'll give David back his quiz. There you go. Marcus, I saw Marcus. Where is he? He's back there. There we go. And Jody's here. And Keith, I got to go regrade his thing. Jared Brunk? Yeah, there's Jared. Okay. There you go. That's from the... All right. Okay. Oh, we're sharing calculators? Just kind of get the QV down there and it'll be okay. It's more of an this week is more of an attendance thing than anything else. I'm taking Peyton Manning's advice from that commercial.
Bigger shirts.
Yeah, it says, how do you get rock hard abs? Also just wear bigger shorts. That's what we're doing. All right, you may go. I mean, well, you can go at any time. You're always free to go. Are you gonna get? Are you gonna get fired because you stayed the entire class time? Oh, okay. You can.